Hello, welcome everyone. So what I plan to talk today to you is about some work we did at Stanford and now we are doing at Pinterest, and it's really about trying to understand relationships between any kinds of items. In this case, we'll think about understanding relationships between products. Okay, so if you think about recommender systems, then really what's the fundamental problem that they are trying to solve is to make items discoverable to your users, right? And in particular, you wanna kind of take and make items discoverable, and especially these rare items that you have many of them in the tail, you really wanna kind of push users towards those. So really, if you think about it, in order to make relevant recommendations, you really need to understand how these items, products, things that you are trying to recommend, how they fit together. Okay, and really the topic for this talk is I want to go and I want to understand relationships between the products, the relationships between items. And maybe traditionally how this has been done is basically if you go on Amazon, they are using user behavioral data by seeing what people co-purchase together and then say, you know, two products are related if they are co-purchased together. But we want to kind of do more than that. Okay, so what we will do is we will take product catalogs. So we'll go and we'll collect data about tens of millions of products, and we'll describe each of these products with a long set of features. So basically, we'll take everything from the product description, we'll take product reviews, we'll take the price, we'll take brand, any kind of attribute data we can think about that product. And what we will then do is we will infer networks of multiple types of directed relationships that describe how these products fit together. And just to be concrete, kind of in the methodology we developed, nothing is kind of tailored to a particular set of products and a particular set of relationships. So just kind of to show this methodology, we decided to focus on two types of relationships. Our nodes will be products, and products can relate using two types, as I said. First one is what we will call substitutes. These are items that are purchased instead of each other, right? So if you are looking at one vacuum cleaner, then other vacuum cleaners, those are the substitute products. And then you also have complements. These are products that kind of you buy together in some sense, or that complement each other. So in terms of vacuum cleaners, it would be vacuuming bags, extension cords, things like that, right? So these are products you purchase in addition. Another thing we would like to do is not only discover these relationships, but we'd like to be able to explain them. In a sense, to say, how do two products relate and how is one different from another? So in this kind of toy example, you may want to say that one vacuum cleaner is quieter or cleaner than the other, or is more high power, and so on and so forth, right? So this is kind of what we'd like to do. So the way we'll think about this, we'll think about inferring a network where nodes are products, and products are connected by two types of relationships, the substitute relationship, here denoted in orange, and then also the complementary or complement relationship, denoted in violet. Okay, so this is kind of what we want to do. Why do we want to do this? Here are 4 reasons why you may wanna do this. So the first one is you really need to, if you want to make good recommendations, you need to understand the things you are recommending, right? You need to understand how they relate to each other. So by inferring the relationship, you really understand the notion of substitutes and complementary goods, and you are able to make better recommendations. Another one is, because we are working with this rich feature data, product reviews, and so on, we can actually go and generate explanations why certain products are preferred over other products, or why certain products are related to other products. So we can go back to the product description or review text to surface that out. Another thing that kind of will come as a side benefit is that we will go and be able to infer this very tightly knit, what we will call micro categories of products, right? So this will be small sets, kind of micro clusters of products that are very, very much related. And here I'm showing just some examples, right? It's like, black t-shirts with a big logo in front of them, or something like very specific, or, colorful sports watches and things like that. Okay? And then the last thing what this allows us to do is it allows us to make recommendations in terms of baskets, right? So I can say, here's a query hat, and we can kind of recommend a suggested outfit in, shoes that don't entirely match here, but, pants and shirts and things like that, right? So we can make these types of recommendations. So now the question is, how do we go and do that? The way we do this is that basically for any pair of products, X and Y, we want to predict whether they are related. And when I say predict, we want to say, are they complementary or are they substitute or nothing of this, right? So what I would like to do is I'd like to have some probabilistic model that, given a pair of products, tells me whether they are related, right? Returns, let's say, probability of them being related. So how will I go do this? it's kind of, the idea is very simple. I'll collect a bit of labeled data. I'll give you examples of, let's say, complementary products. I'll give you examples of substitute products. I'll give you examples of products that are not related. And I'll ask you basically to learn this probabilistic model to make these predictions. Very quickly, it turns out it becomes very problematic because you have labels about what is complementary and what is substitute, but you don't really have labels of what is not related. And if you just pick random pairs of products, then you basically, are trying to learn that a woman dress and baby diapers are not related, and that's kind of too easy of a problem. So you have to be very careful how you generate your negative examples. But once you have these negative examples generated, then what you basically say, I want to maximize the likelihood of the relationships in my network. So you go over all the training data, all the labeled relationship, try to maximize the likelihood of those, and in some sense minimize the likelihood of the non-relationships, the negative examples, right? So kind of very standard. The way you could go do this, right, is basically think products are described by these super long feature vectors, kind of bag of words type things where you throw in your features that you extracted from reviews, from product descriptions, and so on. And it turns out that this kind of doesn't really work, and it's a bad idea. And the reason for that is that really kind of you work with these kind of super sparse things, and it's very easy to overfit. So the question is, can we do better, and how we could go and do better? So here's the basic idea. The basic idea is basically that I want to do some kind of dimensionality reduction, right? But when I'm doing dimensionality reduction over all these long sparse feature vectors, I want to bias my dimensionality reduction in such a way that it's able to explain the product graph, right? So in some sense, what I want to do is I want to do some topic modeling over these sparse vectors, but in such a way that the embeddings I get, the topic memberships I get, are predictive of the underlying relationships, right? Kind of I want to do network inference or network prediction and dimensionality reduction at the same time. And it turns out actually that it's very important that you do these two at the same time, as I'll show you in experiments. Okay, so how are we doing this? Basically, we are putting together two different pieces. We are putting together the piece for link prediction that at the end just turns out to be a logistic regression, where features now are the topic memberships of products, and there we are adding to this likelihood also the term that comes from the latent Dirichlet allocation, which is basically the likelihood of the review corpus. And basically this way we are kind of weighing a way to be able to explain the network structure and also be able to explain the text or the features of the products. Okay, so that's the basic idea. Under the hood, there is much more going on, and there is much more described in the paper, so I just want to kind of pick out a few interesting details that kind of make this really work. So the first thing, for example, is that relationships we try to learn are directed. They are not symmetric, right? So we want to learn both the relationship and the direction. So the way we do this is by actually decomposing this likelihood of a relationship into two parts. One is to say, is there a relationship? And the other one is, what's the direction of that relationship? The way we do this is that basically we learn two kind of independent regressors. One that says, are products A and B related? And the other one, given they are related, what's the flow? What's the direction? And when we are learning this, actually, it turns out to be important that when you are modeling whether the two products are related, you want to take kind of features and multiply them. So basically, you want to do an and over the features, right? We are related because we share this feature. But when you are trying to learn a direction, it turns out that you have to kind of process your features in a different way. You have to take differences, which basically says, do I have more of feature X or you have more of that feature X? And based on that, am I cheaper or are you cheaper? And by multiplying the two prices, you don't learn that. By subtracting, you learn that. So for learning whether there is a relationship, we are using this kind of multiplications of features of the products I and J, and to learn directions, we use differences. And that is a small detail, but actually turns out to be very important. Another question is, right, that I said I want to learn different types of relationships, right, kind of simultaneously. And then the question is, should I learn kind of independent models, one for one type, one for the other types, or what should I do? And the way we do here actually is that we learn one single embedding, one single topic model that is able to then predict both types of relationships. So basically it means we train separate prediction models on top of the features that are unified across the products. And why is this nice is because it allows us to reason about the products for both types in the same space. So that's kind of another interesting thing. And the last interesting thing is that when we are inferring these topic models, we really want to infer lots and lots of topics, right? Kind of not a few hundred, but many more. And by inferring these little topics, what will allow us to do is it will allow us to identify what we call microcategories. And the way we are doing here actually is we are relying heavily on the product hierarchy, right? So the idea is that basically every product belongs to a hierarchy. And when you are estimating topic memberships of that product of that product, all you have to do is estimate the product memberships to the topics that are active because of the path of that product in the product hierarchy. So basically what this means is when you are estimating topics for a charger, laptop charger, you have to estimate its membership to these particular subsets of topics and maybe not the topic about, baby food or something like that, right? And this means basically that we are in some sense sparsifying the topic memberships and the inference task becomes much simpler and we can train much larger numbers of topics. Okay, so there are more details in the paper how to do this, but these were just kind of a few interesting nuggets. The way we tested this was that we went and basically crawled the whole Amazon. Every product that had at least one review, I think we should be able to get. So we have around 10 million products, 140 million reviews. We also asked what does Amazon think is substitute and what does Amazon think is complementary. The way we do this is to say substitute means if people who saw X bought Y, and complementary means if people buy things together. Those may not be the best labels, but that's kind of how we generate labels for our experiments. So that's around the data. So the way we are testing this is now I'll show you a few examples. I'm comparing our approach, which is the last one called Scepter, with several other baselines. Here I'm balancing the data just to make kind of things more comparable. So it's about a 50-50 split. So random does around 60%. LDA basically means first doing topic modeling and then learning the regressors on top, gives you around 70-65% accuracy. Using any kind of collaborative filtering or any kind of category tree information improves upon that, but not necessarily too much. And then our method is in upper 90s. This is both. Here I'm showing you just examples for men's clothing and for female clothing. Here are results just for our method for other categories. So in general, we are around 94% accurate on substitutes and around 90 on complements. It turns out that discovering substitutes is very easy. Discovering complements is much trickier. If we apply this to a kind of a non-balanced data set, rather than now measuring accuracy or something, which would be funny, we are looking at the ranking performance. When you say, given a product, rank me the candidates for substitutes, rank me the candidates for complements. Here I'm showing precision at top k as a function of k, our method, and then other methods, and here there is kind of an order of magnitude or half an order of magnitude difference. There's more experiments in the paper, also some crowdsourcing kind of Amazon type of experiments for this. Another thing that kind of comes as a side benefit, it comes that we can detect topics that are very fine-grained because of this kind of trick with the product hierarchy. So what I'm showing you here is some examples of topics. We manually label them, but you, for example, learn that there are several different types of tablet cases, or you learn that there are several different types of headphones. That is kind of beyond the product hierarchy that already exists. So in some sense, you can think that we extend that for another level. So running shoes, things like that, right? There is minimalist, athletic running, sports shoes, and so on. So that makes also lots of sense. Just to show you a few examples, here is an example of how you could kind of browse this. You are looking at the red belt, the recommended substitute products and the recommended complementary products, and kind of you see it matches in style and so on. So it's not just let's take some random belts and show them, and let's take some other random female-related things. It's actually better. And here's just another example from the graph where now you are looking at a male belt and you see other types of belts and other types of kind of complementary products that go together with this belt. So with this, just kind of to conclude, what I was telling here was the way how you can infer networks of substitutable and complementary products based on the features of products. Kind of the broader theme here is, how do you infer networks from a set of nodes described with a rich set of features, right? So here we focused on products, but you could imagine focusing, if you do this for travel, it would be locations, different types of relationships. So you can have any types of objects, any types of relationships, and you can learn that. The system we developed is called Scepter. Basically, it allows us to infer multiple types of directed relationships between items. We can scale to tens of millions of products, or around 10 million products. And the side benefits we get, we are able to explain these relationships because we have the underlying topic model, so we can look into the words, extract sentences, things like that. And we are relying a bit on the product hierarchy, which you may not have in all the domains, but in our case, it allows us to discover these kind of tightly knit clusters of products. So you could even think of that as making group-based recommendations. So with that, I'm done. Kind of the following slide. Thank you very much.
So can you say a few more words about how exactly you pick negatives? Because you said it's a hard problem, but I think I missed how you actually solve it.
Yeah, I didn't. Good question. So the question is, how did we pick negative examples? It turns out if you pick random pairs of products, then basically you are picking products that are too easy to learn as negatives, right? So what we were doing was we were trying to be careful and go back to the product hierarchy. And use that to say we wanna pick negative examples that are not too close in the product hierarchy but not too far, and this way kind of make the problem harder. We didn't have any principled solution of doing it. That's kind of the heuristic we used.
So as a follow-up question, so do you think it makes sense to pick, substitutes as a negative for complementary relations and vice versa?
Definitely. I mean, sorry, I did. Yeah, exactly. So that is implied. We did that plus the product hierarchy as additional negative examples. But definitely, one thing is that if something is complementary, it cannot be substituted. So we use one as negative examples for the other, plus examples from the hierarchy as additional set of negative examples. Thanks. Good question. Sorry, I didn't say. Yeah.
So in some applications, you may be interested in actually tuning the density of the network after you've inferred it based on the confidence of your edges. So can you talk a little about how you would do that?
I mean, the performance on the ranking task I was showing is kind of trying to do that, right? Basically, you say, I'm at a node, rank me the substitutes, rank me the complements, and now you could decide where you want to cut, and by deciding where you are cutting, you are kind of effectively determining the density of the network. How you do that, I think it very much depends on the application, depends on how do you want to surface this out. Do you use this, for example, as a candidate generation for some re-ranking step later? So then you may want to cut it, I don't know, at 100 or 1,000. If you think of this as maybe a user interface type of thing where you allow people to browse your catalog in this kind of way, you may want to cap it higher up or just show ranked lists. I think it depends on the particular application. Good question.
Very cool idea. Have you thought, it seems like your model, cold start will be a killer app for your model. Have you thought of evaluating it in that scenario?
Good question. Thanks for asking. So cold start. We actually have experiments in the paper about cold start. So what we did was in the paper, most experiments we did was the features came both from product reviews and from product descriptions. But then we also did a set of experiments where we said all we'll take product descriptions. So basically, it can be a brand new product. I'm taking the description. I don't know if it's a book. I take the text of the book and things like that. And things worked actually quite well still. So you can kind of do the cold start problem. You don't need any user data, and you can start learning the relationships. You just need some types of features about these products.
Hi, very nice work. So I have a question about the complementary links. So when you do the regression, right, if you're reinforcing lasso, you're probably going to learn the least minimum attribute that predicts the complementary link. So what does stop you from differentiating. So you're probably going to learn that clothes go well with shoes. What stops you from giving like boots to summer clothes?
What stops me is careful generation of negative examples. So what stops me for recommending winter boots with summer clothes is be careful about the negative examples, right? Otherwise, if I don't have enough negative data, then yeah, I'm learning kind of relationships at a too high level of granularity, so I can be making these types of mistakes. So having enough negative examples turns out to be important, and those allow you then to resolve these kinds of differences.
Thank you.
All right, thanks, Liman.